Hello. Today's video is going to be talking about a feature of organic molecules called aromaticity. So aromaticity is when resonance does resonance. They are relatively stable as compared to many of the other organic molecules we've been looking at, but they are not infinitely stable. There are ways we can react with them. We'll see that in another video. So they're relatively stable because they have these resonance structures which delocalize their pi bonds around the molecule. And you might say, didn't you just simply rotate the molecule? No, if you're trying to look at these color-coded atoms here, you can see that in this case you have a single bond, and in this case you have a double bond. So indeed the bond order for these aromatic species is around 1.5. They're not quite a double bond, but they're also not a single bond. But more than that, you have this bond order that goes all the way around the circle in a ring-like fashion. So sometimes you'll see people draw aromatic rings with a circle inside of them. If you were to look at an aromatic ring, in this case this is a benzene ring on its side view, so you're looking at the side view, you'll see that you have this, this kind of ring of p orbitals. You can kind of think about it almost like a donut of electron density above and below the plane of this flat carbon-carbon bond framework. So again, if we looked on this even further on this, the edge view, where this is the carbon-carbon framework, you have this kind of sandwich where there's a donut of electron density above, a donut of electron density below. And if you need to work on visualizing this, we can try to work on this in class as well. So let's look at how we can quickly assess if something is aromatic or not. Because again, that's going to be what's ultimately typically helpful for you when you're just spotting aromaticity and again the stability that comes with it. First off, it has to be in a ring. The part of the molecule that is aromatic will be in a ring, so a cyclo ring. In that ring, all the atoms in the ring have to have p orbitals. So that is to say that all of those atoms are sp2 hybridized. Also, the total number of pi electrons in that ring and in that pi system has to follow this equation 4n plus 2. That's often referred to as the Huckel equation. So the answers to that could be 2, 6, or 10 electrons. Those are the most common ones that you will see. So again, where n would be 0, that gives you 2. Where n equals 1, that gives you 6. Where n equals 2, that gives you 10 electrons. All right, so let's look at some examples of some systems and decide if they are aromatic or not. So the first one, well, it's a ring, so that's great, but there are sp3 hybridized carbon atoms there, so the second point is not taken. And the third point, there are only 4 pi electrons here, and 4 does not equal 4n plus 2, and so therefore this is not aromatic, for both of those reasons. The simpler one to see is that it's not fully conjugated around the ring. Let's look at this molecule on to the right. Well, it is not a ring, so right away, not aromatic. But let's go through the rest of the process. Is it all sp2 hybridized? Yes, all of these carbon atoms are sp2 hybridized. Does it match the 4n plus 2? There are 2, 4, 6 electrons. 6 electrons does fit the 4n plus 2, so those two portions would satisfy aromaticity, but this again is not aromatic because it's not in a ring. Let's look at this next molecule down here. Is it a ring? Yes. Does it have all p orbitals, or are they all sp2? No, there's an sp3, so therefore it's not aromatic. 4 electrons is also not aromatic. Let's look at this ring structure to the right, where it's now a 5-membered ring, so it's a 5-membered ring similar to this, so it's a ring. That's great. And let's count up the electrons or let's see if these are all in p orbitals. Well, that nitrogen atom has a lone pair of electrons. Those electrons could be in a p orbital, so they could all be in p orbitals, or they could all be sp2 hybridized. And then if you count up the number of electrons, 2, 4, 6 electrons, that does reach the qualifications of being aromatic. Let's look at this compound at the bottom here. This is cyclooctatetrene. So cyclo right into the name, you know it's a ring, so good. The second part is they are all sp2 hybridized, so that's great. Could be aromatic, but it has 8 electrons, which does not fit the 4n plus 2. So this molecule is not aromatic. In fact, if it was flattened, it would be called anti-aromatic. And so as a result, this molecule actually deforms. It sits like a kind of a cup to avoid the anti-aromaticity, which is a destabilizing. So aromaticity is stabilizing, anti-aromaticity is destabilizing. All right, so I'm going to throw in a little bit of bonus material on this next slide to give you a little bit more in depth in terms of why there's energetically why aromaticity is such a good thing. That this bonus material will not be quizzed or tested on, but it's a really good material, especially if you're more on the physical or physical organic side of things. So let's look at the energy landscape of the pi system and look for why these systems are stable. So the energy level diagram for benzene, for this one of the simplest possible aromatic molecules, again it's a ring, it's fully conjugated, they're all sp2 hybridized, there's 2, 4, 6 electrons, that's all great. It passes the quick test. But let's go ahead and fill in the electrons in this chart. So this line here is kind of the break-even line. All the electrons that are lower than this line are stabilizing. Any electrons that are above this line would be destabilizing. So again, this is kind of the where a simple p orbital that is not interacting with other p orbitals would exist. The way I'm going to represent these drawings is from the top down. So if this is a p orbital, you're simply looking at the top of all these p orbitals. So the most stable energy level for any system, any conjugated system, is always to have all of the p orbitals in phase. So there are no nodes in this system. The next energy level up has 2 nodes, and those 2 nodes can give you these 2 degenerate or same energy levels. The next energy level up has more nodes associated with it, and this is how they would look. The next energy level up has the maximum number of nodes, so there is a node in between every single carbon atom, so that it oscillates at a very high frequency, it's very high energy. Again, we can talk more in office hours if you'd like about how we came up with some of these and why they exist. A really convenient and quick way of looking or generating these types of diagrams, at least energetically, is called a Frost-Muslin diagram, where you draw a circle, you draw your aromatic ring or your ring structure into that circle where you start at the bottom of the circle, and so you have a point at the bottom of the circle. So in this case, we put our hexagon in where the point is touching the bottom of the circle. All of the atoms on that ring should touch the circle. Everywhere where the atom touches the ring, there is an energy level. You'll see that this ring structure matches this energetic diagram here. And this works for other rings as well, so you could do this with a 5-membered ring, a 4-membered ring, 3-membered ring. But again, the key feature is you have to make sure you put the one edge or one point of the ring at the bottom of the circle, because there is only one way of having no nodes in a ring. Again, this is a really handy trick for quickly assessing energy levels. We could talk more about it in office hours if that's the flavor of chemistry that you like talking about. I look forward to your questions in class, and I look forward to talking to you in office hours. Thanks.